The idea today is to work on controller design. Imagine that we have a discrete plant. So usually you're given a discrete plant and you have some dynamic specifications. Then how could you design a controller in discrete time? So I've already had a lot of questions about designing a controller in continuous time. Okay. Mainly you can use a comparison of coefficient that is probably not fully clear for everyone, but we will see that again next week. And today we're going to mostly use the root locus method in discrete time that is pretty close to what the root locus method is in continuous time. So that I guess it's a good reminder for every one of you. Probably some people already have really good knowledge about root locus in continuous time. So you're just going to see that it's almost the same in discrete time. So first, the analytical method. The idea is to choose a controller structure. So for example, a PI controller or PID controller, whatever, and then determine using the pole placement method, how could you satisfy some specifications? So where the pole should be located to have some desired output response, for example, or dynamics in your system. Then you need to parameterize the controller. If you're choosing a PI controller, you got two coefficients to choose. The idea is, how could I parameterize the controller to place the poles where I expect the poles to be? And finally, the tester step response. In the second exercise, we're going to see exactly the same, but using a numerical approach this time. The idea is that the root locus can be done automatically by Matlab, and we can directly just add poles and zeros wherever we want and just see where the closed loop poles will be located, also changing the gain, how the step response will change, how it looks like, and try to find a controller this way. So the analytical method is quite nice and handy when the system do not have a lot of, or is not really complex, or where the controller has only a limited number of parameters. But sometimes the problem is much difficult because the controller can have, for example, 10 parameters. And so this numerical tool that is Matlab can be quite helpful for this situation. And in the last part, we're just going to have a quickly look at a sensibility study for model inaccuracy. So if there's one pole of the system that is shifted a little bit, how the closed loop poles will be changed, basically. And the question is my system going to stay stable? So let's start with the first example for today that is centered on the root locus method. In this example, we have a plant, a system called JFP, which is just a plant with 3 poles, one at z equal 0, one at z equal 0.5, and one at z equal 0.75, plus or minus is delta. In the first place, we'll assume that delta is 0, so the system is perfectly known. And then we'll see how, if delta is changed a little bit, how the closed loop poles with the controller we'll have designed will change. The control structure is also defined, so it's k z minus a over z minus 1. So it's as a pole at z equal 1, which correspond to integral action or control action. So that means that you are integrating the control error, which is quite nice to remove the steady state error. And then there's a gain k and a 0 located at a that needs to be defined. The question or the goal here is to control the system to meet some physical specifications. So the first physical specification is the what's called EM, which is the overshoot. So we want an overshoot of 16%. That corresponds to a damping phase factor zeta of 0.5, but we will see that in a second. And we want a rise time of TR equals 7 seconds. We'll also see what the rise time is. And the sampling time is already defined at T equal 1 second. That meets all the constraint that we've seen in the lecture notes, that T is sufficiently small here to capture all the dynamic of our system. The first question is, assuming that delta is 0, find a complex pair of poles or conjugate poles to satisfy these conditions, so mainly the overshoot and the rising time or the rise time. And so to do that, we're going to do that in continuous time, okay? So most of you already know how to do it. I'm just going to make a quick recap here because I know that for some students it's probably a little bit too old, or they've seen that many years in the past. So it's always good to just remember what we're talking about. So the idea of meeting this specification is to identify so-called PT2 behavior. So PT2 is just a transfer function, if you want, with two poles. And these two poles are complex conjugate poles. And these two poles called P1 and P2, let me take the pen. These two poles P1 and P2 should be a conjugate pair of poles. And we know that their real value, the real value of this pole is minus theta times omega n. And the imaginary part is plus or minus omega n, which is natural frequency, times the square root of 1 minus zeta square. Okay. From this, we can also identify alpha here. And so all the poles located on the line here defined by as the same alpha will have the same damping ratio. Okay. And out of these, so we parameterize these poles with zeta and omega n, because using the zeta and omega n definition, we can identify a set of physical properties. So here is output step response of our PT2 elements. And you can see that there's multiple physical elements that we can consider. The first one being the maximum overshoot. So the maximum overshoot is how much overshoot, so how much above the required value, y infinite is the target value, so how much above your output is going to be during the step response. And this is defined only as using zeta. So only using the damping ratio or damping factor zeta, you can already define the maximum overshoot in percent. So it's always directly in percent here in this formula. Then you can also look at the rise time. So the rise time is the minimum time you need to reach the target value. So this rise time can be quite fast, like here compared to the settling time. We're going to talk just in a few seconds. So here you can see that the rise time is just this time here, but the system will kind of stop completely oscillations around here. So you can see that here the rise time is quite fast for this system. Okay. The rise time is a function of the damping ratio and also the natural frequency. So here we have our two unknowns, omega n and zeta, that are in the rise time definition. Then there's the time of maximum overshoot. It's probably used a little bit less often, but still it's quite important. So this is just the time at which the maximum overshoot appears. So this time of maximum overshoot is always larger than the rise time, obviously. And you can see that it's almost the same formula. If you look on into a lecture note, for example, basics of control, it's explained. This formula is derived from the analytical presentation of the PT2 elements. And the only difference is this minus alpha here. So it's kind of a phase shift between these two elements. So whatever the time of maximum overshoot can be also defined as a function of omega n and the damping ratio. Finally, there is the settling time. The settling time is approximately the time where the output of the step response is constrained between two lines. And these two lines are just the expected value y infinite, here it's called like this, plus or minus some delta. Okay, it's not the same delta as the one we've seen before. It's just, I can write it differently. I can write small delta, whatever. And so here we can choose different threshold for this small delta. We can use 2%, we can use 5%, whatever. If we choose delta equals 0, you know that this system PT2 here is designed to be asymptotically stable. So P1 and P2 are on the left half plane. So if delta, small delta here is 0, then the settling time will be infinite. So that's why we usually choose 2%, 5%, whatever, and you have some approximate or some estimation. So here it's just an approximate because otherwise it's not 4, but it's something non-rational that is not really interesting. So already taking this formula here is not exactly 2 and 5%, but it's pretty close. So you can use these formulas. So in the end, we have 2 degrees of freedom when we want to design a PT2, and we need, it's equivalent to having 2 specifications, okay? So for example, in our exercise, we will look at, if I remember well, the rise time and the maximum overshoot. So we will need to use this formula and this formula here to find where the pole P1 and P2 are located, okay? So most of you probably already know all of this, but still it's really important. And also remember that in discrete time, where you want to design some specific behavior, you always identify a PT2 in continuous time, and then you transform this PT2 into discrete time, okay? Now let's go back to our example. So in our example, we want to have a maximum overshoot of 16%. So if we fill everything in the formula I was just showing to you before in the last slide, you can already find this damping ratio, okay? So here damping ratio is approximately 0.5. And then we need to ensure that the rise time is 7 seconds. And we already know what this damping ratio here from this formula. You have also the angle alpha that I've been talking about, which is only a function of damping ratio. And you can come up with omega n, so the natural frequency of the PT2 element we're designing, which is around 0.3. Here, forgot to mention, but it's always radian per second. Here, there's no unit, okay? We can design our pole placement, or we can look where the pole should be located in continuous time, like this. And then we can check if the PT2 element is working as expected. So here we have our PT2 element. So it's omega n square over s square plus 2 zeta omega n s plus omega n square. So this is the definition of the PT2 element. So if you use this transfer function and look where the poles are located, then the poles are always located at minus zeta omega n plus or minus j omega n square root of 1 minus zeta square, and the gain, static gain, will always be 1, okay? In our case, we can compute this PT2 transfer function, and we can plot it as it's shown on the right-hand side. And we can already see, I don't know if I included something, oh, never mind. So we can see here that it's approximately 16%. So we should arrive at 1.16. And the rise time, the rise time is 7 seconds. So here we're crossing 1 at approximately 7 seconds as expected. Okay, so it's not approximately, it's exactly 7 seconds in this case, but it's not obvious to see that on the graph. And now the next step is to discretize this element. So to discretize this PT2 element, I want to find G PT2 in the Z domain. I can just place the poles, or so identify the pole one by one, take a continuous pole and put it into the discrete time, or discrete Z plane, sorry. So for each pole, P1 and P2, I just apply exponential P times capital T being the sampling time in this case. And I find that the discrete PT2 element should have 2 poles located here, so 0.8 plus or minus 0.25, so that the poles in the discrete time are equivalent to poles in the continuous time. So I've also drawn here the PT2 discretized version, so the discretized version of this transfer function in the S domain. And so it's the orange signal, it's a discrete signal. And you can see that we still have the same or almost the same overshoot of 16%, but here it's a little bit slower. It's a little bit slower because to identify the discrete version, I just placed the poles, or I just took a pole in the continuous time and transform it into the discrete time, which leads, as you know, to some distortions, especially phase distortion. So that's why here we got this small gap between the blue and the orange line. Okay. And so the last part that is important is when I design this, so JPT2 of Z, I should find something divided by the two poles. So the two poles here, I don't know what the polynomial would look like, but it's 0.8 plus 0.2j times, or forgot the Z. So it should be like this, the pen. So it's Z minus this, it's not really clear, times Z minus 0.8 minus 0.24j. Okay, so here I'm just placing the poles, and the question is, what should be the denominator? So how do you have any idea how could we find the denominator of the PT2 element in the Z domain so that the static gain of this PT2 element here, the orange line, is still equal to 1? So for that, I've prepared a small poll to just see if you have any idea how it could work. So let me just open the right poll. Should be this one. So can you see the poll now?
Yes.
Yes.
Okay. So just rewrite it differently. It's not fully clear, I guess. If I can clear everything. So the question is, I know where the poles are, okay? So I know that GPT2 of Z is equal to some numerator divided by Z minus P1 hat, Z minus P2 hat, okay? This thing here is just, the denominator is just a second order denominator, it's a second order polynomial in Z. And so the question is, what should be the numerator to have a unit static gain? So for that, there's a couple of proposition here. The first one is that with the same numerator as the continuous time PT2 transfer function. So in this case, we can just reuse 0.1205. The second statement is that in discrete time, the numerator is always equal to the static gain. So that means that we just have to put 1. The third proposition is that the sum of all the coefficients of the discrete PT2 denominator should be used. So it means that I just take here, the denominator is second order polynomial. So it's something like, let's call it alpha 2z squared plus alpha 1z plus alpha 0. And I just take the sum of alpha 2, alpha 1, and alpha 0. The first proposition is to take the last coefficient of the discrete PT2 denominator, to take only alpha 0. Remember that in discrete time is what we do here. And the last proposition is to use the value of the discrete PT2 denominator for this denominator is equal to Z equals 0. So I just take the value here when I plug Z equals 0. So now I will let you, let's say 1 minute to answer this poll. And so that I can see if you have some understanding on this particular point that will be quite important, especially in the next exercise session. Now you should be able to see the results. Most of you answered use the value of the discrete PT2 denominator for Z equals 0. So I guess you try to use the same method as for the continuous time system. I cannot erase, so just remove all the drawings. So why is it not? So it's not the last answer is not correct. So using the PT2 denominator for Z equals 0 doesn't work. And the first hint was that this is the last proposition and the first proposition are exactly the same. If I set a polynomial like this, so just Z squared plus alpha 1 Z plus alpha 0. If I take the last coefficient, it's exactly the same as evaluating this polynomial at z equals 0, because if I evaluate it at z equals 0, then this is 0, this is 0, or this one is 0, this one is 0, and so I also end up with alpha 0. So this is not the correct solution. This is the correct in continuous time, because we know that when omega, the limit of, yeah, I mean, it's not consistent to write it this way, but in continuous time, you all know that when we're considering an infinitely small frequency, then omega is going to 0, okay? So in continuous time, the static gain of a system is always a denominator divided by here the coefficient that is multiplying s to the power 0. So here our static gain is 0.1205 or 0.1205, so it's 1. So in continuous time, you always take the denominator evaluated at s equals 0. That's right. In discrete time now, when you take s equals 0, so infinitely small frequencies, just a constant value basically, then it's equivalent to having z equals 1. Okay, I guess we've already seen that. You can, for example, use this definition. You will end up with exponential 0t, which is equal to 1. So that means that if s is equal to 0, that's equivalent to having z equals to 1. Okay. You can also think of this using the difference equation. You can just go back to the exercise 1 or 2. I don't remember. I think it was second exercise. And if you consider this difference equation, you can also see that z equals 1 correspond to the frequency equivalent to 0. Okay. So here the correct answer was the third one. We take the sum of all the coefficients of the discrete PT2 denominator. So mainly we just evaluate this polynomial for z equals 1, which is equivalent to taking the sum of all the elements. Okay. So this is really important. We will also talk about this next week. Remember that everything related to constant or to an integration is more or less s equals 0. Okay. And that is mapped to z equals 1 in the z domain. Now let's have a look. If I just remove this, let's have a look at the Matlab code here. So nothing fancy. Is it opening? Yeah, now it's opening. So can you all see the Matlab code now? You should all see the Matlab software.
Yes.
Okay, perfect. So here I just defined the specification on the overshoot, maximum overshoot of 16%. And this xi, where is it? Okay, so directly I compute the out of only the maximum overshoot, I can compute this. I call it here xi, but it's just a zeta. So it's the damping ratio. This is the damping ratio. And then I can also compute alpha. Remember, alpha is the angle of the pole. So when you have the pole located here, you have here an angle called alpha. And then I'm using the second specification I want, which is the rise time of 7 seconds. I can compute omega n with a formula which I've seen, and then I can compute the real and imaginary part, which are minus 0.17 and 0.29. And then I can design my PT2 element with the denominator, here numerator, and then using this transfer function toolbox, I got the PT2 in the continuous time. Then I set the sampling time of 1 second, and I can discretize the poles. So discretize the poles is just exponential of the continuous poles time t. And here I'm just computing the real part and the imaginary part. So I've got real and imaginary part once again. And then I design my PT2D, so means in discrete time. Here you can recognize that the polynomial here used is just the roots of, or it's just the polynomials where the roots are the real part plus the imaginary part, or real part minus the imaginary part. This is my sampling time. And here this is just the sum of the coefficient of the denominator polynomial, so that we're sure we have unit static gain. And so if I run everything will be plots. I'm using directly the step command here, and it's taking some time as usual. And it's exactly what we have. Okay, so already what you can see that when we discretize this PT2, our physical specification are not exactly met. Here it's quite obvious for the rise time here that we got a gap, but we can also investigate here a little bit, and we can see that the overshoot is not exactly 16%, but more like 16.25%. So it's, let's say that it's okay for our analysis. Now let's move to the important topic for today's lecture, which is the root locus. Now we know what the specifications are, or we just kind of transform the specification into poles location. And from this poles location, we're going to use we're going to use root locus method to define the zero of the controller and the gain of the controller. So the first step we're going to do is design the zero of the controller. So we set delta to be equal to 0. So the poles are perfectly known. We know that we need to find where the 0A is. We have already 4 poles for our system. So our system is the controller times the system, okay? And I already everything was already factorized anyway, so we already know where the 4 poles are. And we also know the target closed loop poles in discrete time, 0.8 plus or minus 0.2 J, which are expressed here so that we can fill in the equation more easily than just having these numerical values. So the root locus start with the phase condition. The phase condition is always the first one you want to apply. And the phase condition is pretty easy. First, you just plot all the poles of your system. So here are my poles for the system, the 4 poles. Then you have to plot the desired pole. So here, this is my desired pole. It will work exactly the same if I consider taking the one with minus 0.25 J, so the one that is the symmetry with respect to the real part, because we know that conjugate poles are always working in pair. And finally, I have also to plot all the zeros. Currently, the problem here is that the zero for our system is the zero of the controller, and we don't know where it is. So here I just plotted it here, but I could have plotted it here or there or whatever I want, okay? This is to be defined. And what this phase condition tells us is that we need to consider the angle between the expected pole, which is here called Z, and minus the angle between the expected pole and the zeros, and it should match some criterion. Here we want K bigger than 0, so it should match the equation here on top, okay? So to see these angles, let's use some colors. So our desired pole is the red dot, and our first angle is between the red dot and the 0. So here it's just arctangent of our expected pole location, imaginary part of the expected pole location pi star, and divided by the absolute value between pr star minus q1. So in other words, here I'm just considering, take red, I'm just considering here a triangle, okay? I'm interested to look into this angle, let's call it alpha, for example. I know that this segment here is pi star, is perfectly defined. And this segment here on the bottom will be equal to, so if it's in this position, so the 0 is on the left of the pole, then it will be the real part of the expected pole here in red, minus the real part of my 0 that I called it Q1, sorry, because it's a real 0, okay? If we had the 0 located here, then my real part will be, or my segment will be here, and it will be the opposite, so Q1 minus PR star. So that's why here I'm using an absolute value, okay? And so we can make exactly the same construction for all the other angles, so for all the poles, one by one, so the green pole here, then the blue one, the pink one, and the dark blue one. And we can fill everything in the formula. Don't forget the minus before the angle between the expected pole and the pole of the system. And we can numerically compute all the terms, except the one with respect to the 0 that is unknown. And so we end up with this equation here, which is equal to this one, okay? And we have only one unknown, which is Q1. This is our unknown. And so the next step is to say that this should be equal to our condition for k bigger than 0. So condition for k bigger than 0 is this condition. And we have a small k here. The small k here is because we can have some rotations, okay? We are multiplying by 180. I just kept it everything in degree, so 180 degree. But otherwise, you can just say it's 2k plus 1 times 2 pi, times pi, sorry. Times pi, and as k is multiplied by 2, then if I change k, I'm just adding 2 pi every time, and you know, for an arctangent, the 2 pi arctangent is periodic, so there's no problem. So here you can choose any k you want. I choose k equals -1, so that I've got something that is between 0 and 180 degree. And I find that arctangent should be equal to 83.3 degree. Okay, so that means that Q1 is smaller than the real part of the desired pulse. That means that Q1 has to be located here on the left hand side on the real axis. So it has to be located somewhere here. And I can just take the tangent of it and find then, after a little bit of algebra, I can find that Q1 is equal to minus the imaginary part of the desired pole divided by the tangent of 83.3 degree plus the real part of the expected pole. And I find that Q1 should be equal to 0.7729. So on the graph, Q1 is here. It's really close to the pole located at minus 0.75. Okay? Is it clear for everyone? Because this construction is really important. It works exactly the same in continuous time, works exactly the same in discrete time, and you can have multiple unknowns, okay? Here I can say that my controller has 3 unknown poles, okay, and do exactly the same analysis with the angle. And the only difference is that I will find one equation at the end, like this, where there are 3 unknowns. And so that means that multiple or infinitely many solutions, and I just need to find one of them, okay? Now that we find our zero location for the controller, we can look at the gain of the controller. So for the gain, we just use the magnitude condition. Magnitude condition is really easy. It just said that the absolute value of the gain k of the system, which here is the gain of the controller, multiplied by the distance between the desired pole z and all the zeros called q mu, divided by the product of the distance between the desired pole and the pole of the system should be equal to 1. Here we know that k should be bigger than 0, so we can skip the absolute value on k, and we can reorder the expression to find k is just a function of the product of the distance between the desired pole and the current pole, and divided by the product of the desired pole and the 0 of our system. And we have only 1 0, and we know where it is now because we've just computed it before. And now if we apply this formula, we have first the distance here. So the distance here, it's just, all of you know how to compute the distance between 2 points on a plane, I guess. So I just compute the distance here. Then you multiply by the distance here, multiply by the distance here, and distance here. And you divide by the distance of the desired polynomial and the 0. So only this distance here, only one left, which is this one. And you can find the gain, which is 0.1056. So to define the gains, you need to know all the zeros and all the poles of your system, okay? And also the desired pole you want to meet, of course. Now using Matlab, plot the root locus to check the dominance of the complex pair of poles and determine the remaining closed loop poles. To do that, we just plot everything into the equation, then we find the closed loop like this. We set delta equal to 0, we just factorize everything, and we have our first pole, second pole, and third pole, okay? And if we make, I get there's a, yeah, nice. There's a root locus in Matlab. We can find that there's one pole, so our complex poles are located here and there, okay? It's hidden by the box, whatever. And we have two additional poles, one located here and another one located at 0.792 here. Okay. So here is the MATLAB code to compute this. So with MATLAB, the root locus can only help you define. So this method of the root locus can only help you define which k value you should choose. Okay, so let me just show you here. I just it's everything we did just before to compute the angle and k, so it's just the analytical method. And then we can define our open loop system with the k we just defined. And then we can plot the root locus, sorry. And if we plot the root locus, we can remove this. We can see that for a gain of 1, because I already applied the gain to the closed loop system, okay? And we can see that if we change a little bit these gains, we can just look at where the other poles should be located, okay? So for example, if I want this pole, I just change my mind and I want to change a little bit, like for example, having less oscillations, so higher damping ratio, I can choose a gain of 0.5, okay? And if I choose a gain of 0.5, the other closed loop will be located, this one will be closer to 0, and the last one will be closer to 1, I guess. So I need to find a gain of 0.5 and whatever, okay? So this design here, you can look for where the gain of the controller is. So it's only using the magnitude condition, okay? And you can only be on, I mean, probably you already know what the root locus is, but you can only place the poles on the lines, okay? If you want the lines to change, then you need to change the controller 0 that we already found before. Now let's go back to the last question. So a summary is, first we design a PT2 element to just choose where the pole should be located to meet some physical specifications. Then we discretize these closed loop poles to find the PT2 in discrete time, and then we find the controller pole, controller 0 and gain in this case because there were no pole. But if you have to design a controller with a pole that can be changed, then you also need to define the pole. And the question is, what will the real system output will looks like? So if I choose the exact design that we just met, we have the black line which represents on the left hand side the continuous PT2, the green one is the discrete PT2, so we've already seen that, and the blue one is the system. And you can see that the system, remember that here's expectation was 7 seconds, if I remember well. Now it's a little bit more, and the overshoot is a little bit lower. We were asking for 16%, here we probably have only 14% or whatever. So why is that? It's just because in the real system we have more poles. We do not have only these 2 poles, but we have 4 poles, and also because we have a 0. So it's impossible to perfectly follow the PT2 elements. Now we can still change a little bit this gain k. So you have the root locus on the right hand side that helps you see how the poles are changed when we change k, and on the left hand side the system output response. And if we increase a little bit gain, you can see that the overshoot is increased a little bit, but the rise time is decreased. So we can get closer to the expected PT2 behavior by just manually, let's say, optimizing this k gain. So here, for example, you can see that the blue line is closer to the expected green line. Even if here it's not, I'm just taking 1.06 times the gain k we found. So now you can see that the closed loop poles shifted a little bit up. So in the background, it's the initial poles, the desired pole location, and now it's our new pole location. So it's a little bit more oscillations, a little bit faster pole, because we have 2 other poles in our system and 1 0. Okay. And in the same way, we can also decrease the gain. So here it does not really make sense, but we can also decrease the gain. And so our system will be a little bit slower, and the oscillations are also a little bit smaller. Be careful, because when doing that, if you increase the gain too much, you look on the root locus on the right, you can see that at one point, it turns out to be unstable. I'm just leaving the unit circle. Okay, so the oscillation are just growing. At one point, if the gain is too large, it's just completely unstable. And it's the same in the other direction. If you reduce the gain, then you're completely losing this PT2 behavior with oscillation. We have now asymptotically going to the required or set point of 1. And if you removed it too much, so here I just stopped at 0.1K, but if you removed it too much, then the system is really slow. Okay, so this is just to show you that when you enforce some PT2 check, PT2 pole location, still sometimes you have to change a little bit the gain in the end because you have other poles in the system and other zeros. So if we'll have a look here now, root lock is already covered. The step response, so the step response, you can just draw it like this. So this is the initial step response, and we just said that probably having a gain of 1 point, a little bit bigger gain, so like this. It's so I just changing the gain of the system of the controller, and then you can see that the system is a little bit faster and the overshoot is still within 16%. So I can even increase it a little bit more, and I've got something that is closer to the PT2 behavior. Okay. And the final question here is what's happening. So now we've designed our system. We will just take k equals 1, even if we are not exactly following the PT2 behavior. And we're just going to study what's happening if delta is not 0. So if delta is not 0, that means that in the plant here, the pulse that's located at 0.75 is probably shifted a little bit right or left. So shifted on real axis. Here we're only considering the pulse staying on the real axis. And so the pole can be a little bit faster or a little bit slower. To do that, exactly like in continuous time, so some of you already know how to do it, we just take the system, open loop system J of Z, so controller times the plant. Then we find the characteristic equation. So here's the characteristic equation. It's J closed loop is equal to JC divided by, or it's just J, sorry. So it's J, where is it not going back? So it's the open loop transfer function divided by J plus 1, okay? And the characteristic equation, if you just write this as B over A will be this polynomial here. So it's the denominator plus the numerator of the open loop here. And the goal here is to rewrite this expression so that delta become the gain of a fictitious transfer function. So here I just rewrite everything so that delta appears here as the factor. And then what I just do is I just take this as a numerator and this as a denominator of a fictitious transfer function that is this one. Okay. And once you've done this, you end up with a fictitious transfer function, and you can draw the root locus. And this root locus now is the parameter is not k anymore, but it's delta. So the gain here is not k, but it's an equivalent gain that is delta. And you can see how changing delta will place the poles differently. So how changing delta will affect the closed loop poles that you just designed. So just gonna plot this in Matlab so that it will be more obvious. So we define this fictitious transfer function here. And then we plot the root locus from Matlab. So we know that if this delta is 0, then that means that we're located here. So you see that the gain here is almost 0 and the gain here is our delta. So I have my two complex pole. I've got one of the pole here and one of the pole here, okay? And now if I increase a little bit delta, for example, so here I'm increasing it, for example, to 0.3, let's say, then I know that this pole will be shifted to the left when delta increase. This complex pair of pole will be shifted, I don't remember, I guess it's in this direction, so it will be shifted here. And this one here will be shifted here. And the last one that is currently located here, this one will be also shifted onto the right, somewhere like here, for example. So this last pole will be shifted here. So now if I remove all the data tips, what this root locus showed us is that currently my poles, or the system poles, closed loop poles, are here. And if delta is increased, then I see that this one will go to the left, which means that it will be more and more important to consider, because at one point I can have ringing and then even turns unstable. The complex poles are just going into the center, so that means that you will have stronger oscillation but more damping ratio. And the last pole is going to an integrator, so my system will, if delta is increased too much and the poles end up here, then my system will be unstable as well. So here, to do the analysis, what I did is I just ran this a couple of times and created a video out of it, so that we can see how, when changing deltas, the system response is changed. So first, for a negative delta. So if we change delta to a negative value, that means that our pole is located, our pole is faster. So remember that our closed loop poles, one of the closed loop pole was C minus 0.75 plus or minus delta. And so if delta is negative, yes, it was minus like this, if I remember well. So if delta is negative, then this pole will be faster. And so our step response will also be faster. So here, if delta is negative, you can see on the left that the output, the step output, will show higher oscillations, but the rise time is a little bit faster as well. And on the right hand side, you can see that now the root locus is changed. So it's not, when you change the gain, remember that this dot here is just moving along the lines. Now it's not moving along the lines anymore, because we're changing the structure of the system. One of the pole is shifted. It's not only the gain, it's one of the pole that is shifted. So the entire root locus is completely distorted. And you can see that if I decrease this delta too much, so if the pole of the system is changed too much, then eventually it will turn to be unstable. So if I keep increasing at one point, you can see on the root locus that it's almost getting out of the unit circle. And on the output, step output response, you can see that the oscillations are not damped anymore. Now we can do the same analysis for a positive delta. So for a positive delta, then the system will become will show smaller oscillation, but will also be slower. So it's slower because here still the rise time is slower, but the overshoot is also slower. So it's like having a higher damping ratio in that sense. And you can see how the pole, the closed loop poles I was looking for, is also changed. And in the same way, if I decrease it too much, so I've got something that is completely damped at one point, there's no oscillations left. And after quite some while, you can see that the root locus, there's not even a conjugate pair of poles. So you can see that here, exactly here, there is no more poles here. So that means that all my poles are on the real axis in this case. And eventually one pole, this one I was talking about beforehand, is moving towards -1. And so if I keep increasing this delta, this pole is really, really close to -1. So I start to have ringing. And at the end, it just goes out of -1. And so I have an unstable system. So I've got oscillations. This is called ringing. And you can see that the amplitude is like growing like this. So the envelope is growing. And so my system is completely unstable. Okay. So this is just to show you, if one of the system poles is changed a little bit, you can quickly, using the fictitious transfer function, look at how the closed loop poles will be changed. Is there any question regarding this? Everything I've been talking about in the exercise 1. So I know that for some of you, everything is pretty clear because you already did it in continuous time. But still, I guess it's quite good to have a quick recap. And you can see that in discrete time, the only things that's different here so far is that you can have ringing if one pole is close to -1. And the other difference is how to compute the steady state gain, which is for z equal 1, denominator z equals 1, and that's s equals 0, so not z equals 0. If there's no question, we can move to the first question, which will eventually summarize what I've been talking about. So this question is quite simple. The root locus method can be used with a discrete time system for, or with discrete system for, and you have to find that only one wrong answers. All the other statements are perfectly correct. The first statement is that defining the controller parameters to place the closed loop poles to a specific location. So I can use the root locus to just choose the controller parameters that the poles are located at a specific location. The second is that I can place the closed loop 0 to a desired location. The third one is finding the controller gain with a magnitude condition. So I can use a magnitude condition to find the K for my controller, usually defined as K. And the last statement is you can find the controller's poles and zeros and the remaining closed loop poles if there are more than 2 poles. So this last statement is just saying that you can find all the poles and zeros of the controller and also the remaining closed loop poles of the system if there are unknown. So just let me open once again the poll. So almost every one of you said or answered the second, choose the second statement, which is the correct one. So I would just go pretty quickly on the solution in this case. So defining the control parameters, of course you can, it's what the root locus method is used for. Finding the controller gain with the magnitude condition is also what the root locus method is about. Remember that magnitude condition here is for the gain K, and the angle condition or the phase condition is for the poles and zeros. And so this last statement here means that if I've got a controller like this, for example, S plus A, S plus B divided by S plus C, S plus D, okay, this will be my controller. Then I can use, or it can also be in discrete time, it's a discrete lecture, so let's put it C, doesn't change anything. Then I can use the angle condition to find A, B, C, and D to meet a closed loop pole, okay? And so finding the closed loop zeros, no, why is it not true? Because the closed loop zeros in a single input, single output system are always open loop zeros. Remember, J open loop of S or of C, whatever. Then I know that J of closed loop will be equal to J of open loop divided at 1 plus J of open loop. If I write this J open loop being equal to B over A, then J of closed loop will be equals to B over A, 1 plus B over A, and I can factorize by A and say it's B over B plus A, and my zeros are the zeros of B, which are the zeros of my open loop, okay? So placing the closed loop zeros is not true. The only thing that's true in here is that if there's a 0 in the controller, then here in this step here of the phase condition or angle condition, you can, or you are looking for where to place the zeros of the controller. And so if there is infinitely many solutions, you can place the zeros already where you want and then still ensure that the closed loop poles requirements are met. But this is just a special case. So this is not what the root locus is used for. It's not for placing the closed loop zeros. Okay, so nice. So that means that almost all of you get good understanding now of root locus. If there is no question, we can move to the second exercise, which will be shorter.
I have a question concerning like a general understanding. the PT2 behavior is neither the behavior of the plant nor the behavior of the controller. So it's the behavior I want to have for the whole system, right?
Exactly, yeah.
Okay.
So the PT2 behavior here, it's not in this slide, it was on the previous one. It's what you expect from the system, but remember that the PT2 behavior corresponds to a transfer function with 2 poles and no zeros. So in our system, we have more than 2 poles and probably some zeros. So it's impossible to perfectly follow it. Okay, it's exactly the same in continuous time. So the PT2 here in green is the target, and we're quite close to the target. But because there's more poles than 1 zero, it's a little bit slower. So that's why we can, for example, I propose to increase a little bit the gain, but it's eventually not possible to exactly follow it. You're right.
Okay, so the system in our case behaves more or less like a PT2, but it can be that the remaining poles and zeros, I would say, mess it up, or is it
Exactly.
possible? Okay.
So when you look at the close loop, it was a question before. I was probably a little bit quick on this one. Yeah, it was this question here. We always need to check that the complex poles here are the one that follows exactly the PT2, okay? Then there are some zeros on top of it. So here there's a zero here at 0.75, for example. I cannot change it anyway. So if the zero here is, for example, really close to zero, probably can change completely the output, but I cannot act on it. And it's the same for the remaining poles. Here, there's a remaining pole here, so it's okay because it's really fast pole and it's not close to -1. But if this pole is, for example, here, then it's a problem because it's a pole that is slower than the conjugate pair of poles that we want to enforce, and it will cause ringing, okay? So here we're quite lucky because the 2 remaining poles, this one here also can be considered as not dominant poles. Here the dominant poles are still the one from the PT2, are these 2 poles, okay? So when you're using the root locus, you're right, sometimes you design a controller and you end up with 1 pole here, and so it's absolutely not following the PT2, and that can be a problem with the root locus method.
Okay, so when I'm just unlucky in real life, so I have to simply change to another controller, or
whether you choose another controller with more parameters. So for example, here you can use a PID controller where you will have 3 parameters instead of only 2, and so you have more degrees of freedom. You can also change the location of the desired poles. But yeah, mostly you need to change the controller in that case. Or use a completely different method, like for example, model flowing control, that we're gonna have a look at in the next week. And it's quite nice that you mentioned it today, that here, when you designed a controller with a root locus method, the plant zeros, for example, will always stay the same. So that means that the plant zeros, if you have a zero of the plant that is quite slow and that completely change the output or completely define the output of the system, then you can use any controller you want. Not any, but if you use a PI controller, for example, using the root locus method, you will always have this zero of the plant that will stay at the same location and that will cause the system to not behave as expected. And that's why we can, for example, use a model following controller that we will see next week to kind of remove this zero of the system to have exactly the PT2, or to get really much closer to the PT2 behavior. Is there any other question?
thank you.
If there's no more question, we can move to the second exercise, which will be the numerical application. So the idea of the second exercise is we have a plant system which has 3 zeros in continuous time, then we discretize it with a zero order whole. So you all know how to discretize the system in the order whole and express it in the Z domain here. And you end up with a third order polynomial. So you will have 3 poles on the denominator, and you will have here I think there is a no, it's positive power of z, so you will have 2 zeros and 3 poles, okay? And the question is, you need to design a controller. So you need to design j of z is equal to something, but this something will just, in the most general case, j of c in the most general case will be some gain k times some zeros location, let's call it q, and some poles location, so some c minus poles. And the question is, if you don't know how many zeros and how many poles you need, how could you design a controller so that you have some specifications? So probably you have a maximum number of zeros and poles. You want the system to be sufficiently fast, for example, so can be like the rise time should be, I don't know, faster than 1 or 2 seconds. You want to have a system that is not too much complex, so you don't want to have 1,000 zeros and 1,000 poles. You can also have some problem with saturation of the controller, so you don't want to have really fast controller, for example, or you don't want to have ringing, so the controller is smoothly actuating the system. You can have also precision sensibility, so if one pole of the controller is really close to 1 0 of the controller, then it can be quite difficult to have that, to match exactly this behavior in real life. And you can have a bunch of other specifications. And when you have this system, you can see that here the root locus method is not enough. There's too much complexity here. So we definitely need to look at what's happening when we're just placing some poles and some zeros for the controller. And this is exactly what Matlab can help us with. So here I just defined the sampling time. I define the system in continuous time, and then I define the system is discrete time using the C2D function that just express the system in discrete time using a zero order hold. Yeah, this is my zeros are located in 1 and 0 minus 0.97, and my poles of the system are located at 1.044. 0.96 and 0.90, so one of the pole is not stable, and we're going to use this RL tool. So this RL tool is a toolbox that you can have here somewhere. You can download it. I don't know the name of the toolbox, but yeah, you should be able to find it online. I guess it's a toolbox. It's part of the control toolbox in Matlab. And so if you open RL tool given j of z, then it will open you this window. And this window represents a system like this. So it's exactly our system in closed loop, where j here is the plant that we specified. H can be anything. We're just going to set it to 1, so we're just going to ignore it. The noise, we don't care as well. The prefilter, we still don't care. Prefilter, we can just set it to 1 as well. And C will be our controller. And here's the goal, is to define C numerically. So we're just going to try some values for C until the closed loop meet all the specifications I've been talking about. So to start with, let's look at F. So F should be equal to 1 because I want to ignore it. H is also equal to 1. So remember that H is a feedback term. Where is it? H is a feedback term. And our controller currently is set also to 1. The controller is doing nothing. Okay. So we have our closed loop represented here. Where is it? So in the root locus, sorry, we can find that currently with a gain of 1, the closed loop poles are located at 0. Something close to 0.9 here. I cannot see the actual value, but it's close to 0.9, close to 0.97, and one pole is unstable at 1.05. And the last pole is located here. It should be 4 poles. Where is the last one? Okay, the first poles is located somewhere. It's probably overlapping with one that's already existing. So never mind here, the first thing we can do is change the controller gain. So if you look on the right-hand side, you got the step response, which is unstable because of this pole. And if we change the gain K, so I just move here the red dot, that's equivalent to changing the gain. You can see that it's impossible for me to move this pole inside the unit circle. So it's impossible to move this pole inside here. This is a unit circle delimitation. And it's impossible because this pole will always stay on this branch, and this branch starts at 1.05 up to infinity. So that means that first of all, if my controller is only set as a gain, static gain, I cannot have a stable closed loop. So here what's quite handy is that I can add some specification for the controller. To do that, I edit, so it's called the compensator in Matlab, but it's just a controller. And I can add some poles and some zeros of the controller. So here, for example, I'm adding a pole here, a real pole. So I can add a real pole and I can see how the root locus is changed when I had a real pulse. And you can see that if I add a real pole here, for example, then the problem stayed the same because this pole here will always remain unstable, whatever gain of the controller I choose. So adding one real pole here doesn't help at all. I can also add complex pair of poles. I'll just remove this one. I can add a complex pole if I want. I can also choose the location of this complex pole. But once again, you can see that it's impossible to modify the unstable pole. I cannot, using a conjugate pair of poles for the controller, I cannot change the this pole here will always remain unstable. Also, you can see that now I'm adding two poles for the controller, so my closed loop will also have two additional poles. So mainly this one here and this one here. That is also a function of the controller gain. And finally, I can add some zeros for the controller. Let's demonstrate this. So I can remove this one for now on. I can add a real zero or a complex zero. Let's go for a complex zero. And now with a complex zero, you can see that I can try to attract my poles and place everything inside the unit circle. So here, one possible controller, for example, can be this one, okay? And here I've got my 4 poles. Yeah, 3 poles are located here. So you can here see that there's a complex pair of poles inside unit circle. There's one pole here. There's no more pole on this section because if I unzoom, you will see that there's some kind of branching like this, if I remember well. So let's unzoom. You see that there's now some branching. So the pole that was going to infinity now is able to freely move here and then there and come back into the unit circle. So this is what we call branching. So here I'm creating some branching so that adding these zeros to the controller will make my closed loop stable for some gain. And of course, for some other gain, if I increase the gain, if I decrease the gain here, it becomes unstable. And so now I've got 1, 2, 3 pole, and the last one is on the left of the graph, but is also stable. It's here. It's close to 0, so this one we pretty much don't care. Okay, so this is one possible design of a controller. You can see now the step response. I can change it a little bit, whether by moving the zeros of the controller. So everything is just done by drag and drop here. You can also specify the numerical values, of course, if you want some. So for example, here you can specify the damping ratio of 0.8, and you can specify natural frequency of 15, for example. And then you can change the gain of the controller to make it stable again. And now you have the desired damping ratio, it's not exactly to have exactly the damping ratio. You should have an infinitely large gain, of course, to be at the 0 location, but still you can be sufficiently close. And you have the system response on the right-hand side. So this is how you can use this Matlab toolbox. Now you still have to be careful. If I go back to the PowerPoint, here I've got only 2 zeros, so I guess it's okay. My controller is not that complex. The reaction time is not that fast. You can see that it's taking a few seconds. I don't know. It's taking like 2 seconds, so it's probably, let's say it's completely fine for my system. Complexity, we already said it's quite good. Amplification, let's kind of ignore it currently because it's mostly going to 0. But still, there's another problem here. Can any of you say what the problem here is if I design these specific controllers? So my controller is just here, it's given here. Can any one of you say why this is not possible to have this controller in the system? So remember, the step response is stable, so it's perfectly fine. It's all the closed loop are here and there's another one there. So according to you, what is the current problem here for this design? Does any one of you have an idea?
Actually, I'm wondering why in the step response the value is approaching 0.
That's first element. Yeah, that's interesting. That's a good point, and that's not directly linked to the fact that the controller is not feasible. But that's one point. I can, for example, change a little bit. Sorry, if I add a real pulse. Sorry, no, it's not working anymore. So basically, the fact that we are approaching 0 means that we have, for the system, we add 3 poles for the system, 4 poles, and now we have 3 zeros. And so here it just means that the static gain of the system is 0. Okay. So when you have this kind of behavior in continuous time, it's called a differentiator. So the static gain is 0. So the output is non-zero every time the input is changing. Okay, so it's, for example, if I take s plus 1 divided by s plus 2 in the continuous time, the static gain here will be 0. So this is not really a problem here. So if you just look at the controller expression here, can you say anything special about this controller? This controller here is just j of controller of z is equal to a numerator. So here it's z squared plus something d plus something, whatever, divided by 1. And so this is not causal controller. I'm just having a controller which consists of 2 zeros and no poles. So this is not causal, so this is not realizable. So the plant is perfectly fine because I've got 3 zeros and 3 poles, or even I think I got 4 zeros and 4 poles. And so the plant is still causal, but the controller is not. So when you're adding zeros and poles, it's not in the PowerPoint, is it? I don't remember. But one thing is it has to be causal. So that means that the controller, for the controller, the number of pole, let's call it number of pole, should be bigger or equal than the number of 0. Okay. And most of the time it should have to be bigger than the number of 0 so that it's strictly causal. Okay. So now, for example, even if I design this controller here, I still have to keep in mind that, for example, here the controller is not feasible. And as you also mentioned, that the step response is going to 0. That is probably also something I don't want. And the tricky part is, as I just demonstrated a couple of seconds ago, that if I just add 2 poles, for example, then you see that once again, one of the closed loop 0 here is unstable again. And so you can see that it's not that easy to add some zeros and some poles in a way that the controller is feasible and the closed loop is also stable. So here, adding 2 zeros and 2 poles, probably you can change a little bit the 0 location if I can do, but I cannot create branching anymore. You see? And this is one of the problem. Even if I create branches like this, one of the pole is still on the right-hand side of the screen here. it's, where is it? It's here. This one is always unstable, you see? So the one here will always remain on its branch here and will always be unstable. So you see that this is quite powerful. You can add as many zeros, as many poles as you want, but still it can be quite tricky sometimes to find all the poles, closed loop poles being stable, to have a controller here that is feasible. So same number of poles and zeros or more poles than zeros that have a step response that is stable and probably not reaching zero, for example. And so even if this is really powerful, it can be really tricky to use. For this specific application, here I'm going to propose one possible design. So there is infinitely many designs. I'm just going to propose one, which consists of adding only one pole and one zero. So the goal of adding one zero is to create so-called branching, so that my pole on the right-hand side of the unit circle is now entering the unit circle. And adding a pole is just to make the controller causal, and so we can realize this controller. So now if we just have a look at this method, the idea is, I'm going to remove this one. So the first step is create branching. And to create branching here, I propose to add a pole at 1.0, or first add the zero. So add a zero between plant zero and pole. So the first zero, I'm adding it at 0.98. So add a zero. Where is it not adding? Real zero at 0.98. And then add a pole at 1.01. Then I add a pole at 1.01. So to design this one, I just tried different pole and zeros location to see what's happening. And I come up with this system here. And here you can see that, interestingly enough, it's possible to just map all the poles that were located outside of the unit circle are now entering the unit circle here. Okay, and so I choose the gain of k equals 10 from well. So if we pick up k equals 10 somewhere like this is the setup, more or less the setup that I choose, where I've got a stable step response and all the poles are inside the unit circle. If I unzoom, there's still one last one, but there's some branching, so it's quite difficult to see. But the pole on the left hand side here the pole, they're just going like this, and they are mapped back here. Okay, so there is no pole here, no problem, no pole for this controller gain. Okay, and if I go on Matlab, this is why on the PowerPoint you end up with a controller like this one, where you have 1 0 and 1 pole, so it's something we can realize. The gain is not that high, it's not 1000 or 2000, for example, so it should be okay in terms of input saturation, and the closed loop poles are perfectly stable. So there's 2 closed loop poles here, and there's also 2 other, so this is a closed loop poles that are the dominant one. That's why you have these oscillations, and there's 2 other poles that are located, if I zoom in, so these one are the dominant one, okay, and there's these 2 additional poles here that are not dominant. Okay, so here this is just one possibility. You can play with Matlab at home for this system or another system and try to find where to place the poles and the zeros of the controller to have all the specifications you want. So let's move to the last question for today. So using the root locus representation, one can design a controller, so placing the poles and zeros just as what I've been doing, and determining the controller gain. So the idea is to find the wrong statement once again. So using this method here on Matlab, for example, You can plot the step response to investigate if the dynamic requirements are met. You should avoid placing a pole and a zero at the same location. You can try to place closed loop poles, or you should try to place closed loop poles away from -1 to avoid ringing. And you should make sure that the controller does not have more poles than the plant. So there's only one wrong answer. And I'm just gonna start the poll again. Relaunch polling. Yeah. So please take some time, or let's say 2 minutes, to try to investigate which of this statement is wrong and why is it wrong. This one is probably less obvious to answer. First statement was plus the step response to investigate if the dynamic requirements are met. Obviously, it's really important to do so. So it was not the wrong one. Avoid placing a pole and a zero at the same location. So some of you answered this one. This is not also a wrong answer. The idea behind this, avoid placing a pole and a zero at the same location, that if you look at your controller, so let's say that my system is controller times the plant, okay? If I design the controller to be C minus A over C minus A, then I'm just complexifying the controller. Okay, the controller here will be complex because it will have, so probably something more here and more here like this. So there's like 2 zeros and 2 poles, but having 1 pole at the same location at 1 0 is strictly speaking equivalent to just removing this pole and 0. So it's just increasing the complexity of the controller. Now, the second thing that is important is if I said now that the plant has 1 0, for example, at Z minus A, I can say, okay, my controller will be Z minus A and then Z minus B. And so my open loop system will have only 1 pole, and so my closed loop will also be simpler, okay? If you do that, the problem is that in J here, you will end up with Z minus A over Z minus B times Z minus A. And so you'd say, okay, these one are canceling each other. The problem, as we've just seen before, that the plant's pole is probably not exactly at A, but it's probably Z minus A plus some delta. And so if the plant pole is shifted a little bit, then you will start having this zero that is not, this zero here is not compensated anymore. And so the closed loop can be significantly different. So always try to have no pole and zero at the same location. Then the third statement was try to place closed loop poles away from -1 to avoid ringing. We've already discussed about it. If one of the pole is located close to -1, so let's say that this is the expected behavior, then I may end up with something like this, okay? So here it's just to get the idea, I will have some lots of really high frequency oscillations. So I should also place or try to not have any closed loop close to -1. And so the right answer was the last one. Make sure that the controller does not have more poles than the plant. Indeed, we don't care. Okay, if I just take a plant, so G controller is equal to, let's say, Z minus A over Z minus B, Z minus C, Z minus D. This controller is perfectly feasible. Okay, it's perfectly causal. 1 0 3 poles, all at different locations, perfect. Even if my plant is 1 over C minus 1, for example, then here the controller is higher order than the plant, but this is not a problem. It can be a problem for the controller complexity, but it's not a problem in terms of causality or in terms of feasibility. So you always make sure that the controller does not have more poles than zeros, but the complexity of the controller has nothing to do with the complexity of the pole. Controller can be way more complex than the system, sorry. It's absolutely not a problem. Okay, so now just let's move to the conclusion for today's session. We've been investigated some expectations and how we can, or which kind of method, tools, or knowledge we can use. So first, we looked at where to place a closed loop pulse to meet dynamic specification, and we've seen that we can design an ideal PT2 in continuous time and then express it in discrete time. Then to parameterize a controller with a root locus method, we can use the phase and magnitude conditions, phase condition for placing the poles and zeros, magnitude conditions to find the controller gain. Then to explain what the dynamic specifications are not exactly met, it's because the system has more poles, probably also has some zeros. So we cannot, I mean, the two poles that we enforce to the system that come from the PT2 are probably not dominant anymore, or still they can be dominant, but there's some extra dynamics of the system that makes it diverging from the PT2. Then we studied the sensibility of the model parameters. So you just have to express this fictitious transfer function exactly like in continuous time, and then draw the root locus with respect to this fictitious pole shifting. So we called it delta in the exercise. Finally, we've seen the Matlab toolbox RL tool, so we can manually design a controller. We can place the poles, the zeros, look at the root locus, look at the step response. We can also look at the impulse response, look at the body plot with the phase margin. I haven't shown that to you, but you can just investigate that on the tool. Everything is really easy to find. So you can also look at the phase margin, the gain margin, whatever you want. So it's really handful, but it can be sometimes quite difficult, as we've just seen in the example. And the last one was understanding the pole placement impact on the step response. So is it going to be stable and stable? Of course, I want it to be stable, but then what is the kind of damping factor? What does it mean? Natural frequency of the system. Just define how much oscillation I will have. Also, if I'm close to -1, I can have ringing, and all these all these elements here are really important, and you can use this Matlab Toolbox RL tool to investigate where you're placing the poles, how the step response, for example, is changing, and so get some kind of intuition. This is really important to have some intuition on how, if I move the pole on the left, on the right, on more or less imaginary part, is it going to change the damping factor, the frequency, whatever. This is really nice to play with. So do you have any question for today's session regarding what we did today, regarding what we did in the previous sessions, or any general remark? Otherwise, I would just, it's already 5 minutes after 11:30. So I would just thank you everyone for being here today. And just remember that this afternoon it starts at 1:30, not at 1 as usual. So now if you don't have any question, then see you this afternoon, and see you also next week.
Thank you. See you.
Thank you. Bye.